Okay, so let's start today's lecture, a tutorial, a sort of tutorial about sound scene understanding. So now we are talking about the blind source separation mainly, and so the basic technique is based on statistical modeling of single channel and multi-channel audio signals. And this technique is used for source separation, speech enhancement, and de-variation, denoising, which is assumed to be used in the real world. And also, we introduced some very interesting extensions to this basic technique using deep neural networks. Okay, so this is, in my talk, I will introduce the very basic formulation of statistical modeling for audio signals. So in my part, we will not introduce any deep learning techniques. So I will talk about the very basic, the very basic fundamentals of statistical signal processing used for multi-channel source separation. Okay, so the title is the Unified Theory of Blind Source Separation based on independence, non-negativity, and low-rankness. So here is the agenda of my talk. So first, in the first part, I will introduce single channel blind source separation method. So there are two major approaches to single channel BSS. The one is full covariance modeling. The other is joint diagonalizable covariance modeling. And then based on the technique developed for single channel BSS, I will introduce multi-channel blind source separation method. Okay, so this is a very fundamental background of the in the field of signal processing. So the single channel source separation is a fundamental task for many applications, including automatic music transcription and the singing voice separation in the field of music information processing. So the popular approach is to blind source separation is to use time frequency domain decomposition in the short time Fourier transform domain. So as you can see, at the beginning, you can get some audio signal in the time domain like this, and then usually you can perform the Fourier transform to get such a complex spectrum in the frequency domain, which consists of real part and the imaginary part. And then usually you may ignore the phase information and get only the absolute value like this. So because the low rankness and the sparseness, which are important characteristics of audio signals, are useful clues for decomposition in the absolute value in the power spectral domain. So that's why you ignore the phase information usually. So based on this approach, a non-negative matrix factorization has been one of the most popular approaches to audio source separation. However, there are several related studies on phase-aware source separation method. So, for example, complex NMF or high resolution NMF can consider phase information somehow. So and these methods are additivity and consistency aware methods for blind source separation. And please note that the phase and magnitude values cannot be determined in an element-wise manner. So this means that So the time frequency covariance modeling is very important to improve the performance of source separation. So previously, so there are several methods that can deal with the covariance structure over the time frequency domain. So in this talk, I will introduce each of these methods one by one. The first one is a very popular technique called non-negative matrix factorization, NMF. So NMF has widely been used for audio source separation. Here, you can, so this is the observed mixture in the time frequency domain. This is the time axis. This is the frequency axis. So please assume that this is the power spectrogram in the time frequency domain, which can be obtained by ignoring phase information after the short time frequency transform to the time domain signal. So then you can calculate the power spectra at individual time frames like this. So these are power spectra. What NMF does is to find such non-negative vectors. So this is called basis vectors. This is called activation vectors, such that so each non-negative vector, each non-negative mixture vector is approximated as a weighted sum of basis non-negative vectors like this. So there, for example, so here, if you focus on this vector is approximated by a weighted sum of these three basis vectors, where the weights of these vectors are determined by these activations. So in this case, for example, the first one and the second, the first and the second basis vectors are activated, and the third basis vector is not activated. So these are weights. Here, so this is the observed mixture. So this is the power spectrum, and this is a reconstruction because this is a weighted sum of basis vectors. So here, our objective is to minimize the Itakura-Saito divergence between this observation and the reconstruction. So this is a very basic formulation behind the NMF. So however, so in this formulation, surface information is not used at all. To solve this problem, the positive semi-definite tensor factorization was proposed. So in this method, we calculate the covariance matrices at the individual frames. So this is different from the previous NMF. So in NMF, in each time frame, we calculate the power spectrum, right? Power spectrum by ignoring phase information. On the other hand, so in this method, we calculate the covariance matrix at each time frame. So this is the covariance matrix xt at time frame t, which is given by the product of the complex spectrum and the product of the complex spectrum and its conjugate transpose. So ST is a complex spectrum. So in this case, so we don't ignore phase information. So XT is a complex matrix. So the phase information is incorporated in this representation. Given a set of these observations, our goal is to find such basis matrices and the activation vectors. The activation vectors are the same as in the same as NMF. However, so the basis vectors are extended to basis matrices in this formulation. So here, for example, so YT, the covariance matrix at time frame T is approximated by a weighted sum of basis matrices, where the weights are determined by these activation vectors. So here, there's some divergence between the observation and the reconstruction is minimized. So this is the objective of this method. So, this is a very natural, mathematically natural extension of Itakura Saito NMF that can be used for audio signal modeling. So this figure shows the comparison between NMF and the PSDTF. So this is the observation. Here, this indicates a complex spectrogram. So each time frequency beam has some complex value. So in NMF, in PSDTF, we calculate the powers covariance matrices at individual time frames like this. And then we want to find such basis matrices. So here, if you focus on only the diagonal elements like this, so this PSDTF formulation reduces to the standard NMF. So focusing on only diagonal elements means that we ignore the covariance structure between frequency beams. So in theory, all the frequency beams are independent, right? So this is the conclusion of the standard Fourier transform theory. So because the time domain signal is completely stationary. The infinitely long time domain signal is stationary. If you apply the Fourier transform, all the frequency beams are independent. However, the real-world signal is non-stationary. So this means that if you apply the Fourier transform, there must be some covariance structure between over the frequency axis. That's why it's very important to consider the Fourier frequency domain covariance. The covariance structure in the frequency axis in source separation. So this is the comparison in terms of mathematical modeling. So here in NMF, each non-negative vector is approximated by a weighted sum of non-negative vectors. On the other hand, in this extension, each positive semi-infinite observation mixture is approximated by a weighted sum of positive semi-infinite basis matrices. So this is a very elegant correspondence between these two methods. And the problem is that which criterion should be used for evaluating the approximation error between the observation mixture and the reconstruction. So in statistical audio signal modeling, so it is well known that Itakura Saito divergence is theoretically suitable. So and the corresponding divergence in PSDTF is log determinant divergence. So this is the matrix extension of the Itakura Saito divergence. So in Itakura Saito divergence, you can evaluate a distance, some kind of distance between two non-negative vectors. On the other hand, the log determinant divergence evaluates some kind of distance between two positive semi-infinite matrices. So this is a very elegant correspondence. However, in this PSDF model, so we can consider only the frequency domain, frequency covariance structure, right? Because here, each basis matrix represents a covariance structure over the frequency axis. However, the activation vectors are the same as those used for standard NMF. This means that there are no covariance structure in the time domain. So only the covariance structure in the frequency domain, the vertical axis, is considered in this modeling. So the question is how to deal with the time domain covariance structure. The naive way is to deal with the time domain covariance structure is to just transpose the mixture spectrogram like this. So this is the time axis. This is a frequency axis. You can just transpose this complex spectrogram. And then you can calculate the covariance matrices at individual frequency bits, not time frames like this. And then these are observations. And then you could find some basis matrices in the time domain. And this is the activation. But actually, this is the basis vectors used for NMF, right? So because so this is the frequency axis. So this is time by time. This is the time by time matrices. So, however, in this modeling, it's okay to deal with the time domain covariance structure. However, the frequency domain covariance structure cannot be dealt with in this modeling. So either the time domain or frequency domain covariance structure can be dealt with in this PSDTF-based modeling approach. So you might focus on the vertical covariance structure, or you can focus on the horizontal covariance structure in this approach. So how to deal with both covariance structures at the same time? This is a main research question. So to do that, we have developed correlative tensor factorization, CTF in short. So here, in this model, both the frequency domain covariance matrices and the time domain covariance matrices can be dealt with simultaneously. So actually, this is the formulation. So X is the observation. So there is only one observation here. So X is the so X is the X is an observed positive semi-infinite matrix, which can be obtained by calculating the product of S and its conjugate transpose. So here, S is obtained by serializing all the TF bins of the complex spectrum. It's a very huge vector, right? So actually, this is a mixture complex spectrogram. So there are TF bins in this matrix. F frequency bin, T time frames. So there are TF time frequency bins in total. So you can serialize. You can list all the TF bins in a line, and then you can get a very long, very huge, long, complex vector S. Using this S, you can calculate the observed matrix like this. So this is the FT by FT. So So typically, so F is several thousand, T is several thousand. So it's a very, very huge matrix, very, very huge observation. So given this observation, our goal is to find a set of frequency domain covariance matrices and a set of time domain covariance matrices like this. So this is the this is a very basic formulation behind the CTF. And you can see that this is a very elegant mathematical extension of Itaquera-Saito NMF. So actually, you focus on only the diagonal elements like this, so you can recover NMF formulation from CTF formulation. Yeah, and let me introduce briefly how to estimate the parameters of CTF. So you might know that there are some very efficient closed form updating rules can be available for Itaquera-Saito NMF. So actually, anyway, we have to use some iterative optimization technique for parameter estimation. So Itaquera-Saito NMF, so for example, W basis vector is updated by using this formulation. And also the activation can be updated in the same way. So in CTF, so the frequency domain covariance matrix and the time domain covariance matrix can be updated in a closed form like this. So and here, this operator is a geometric mean of two positive semi-limit matrices. So we found that we found such a very interesting correspondence between NMF and CTF. So and there is a very interesting concept. The geometric mean of two matrices is a very interesting concept. So this is a very so here this is a natural extension of this updating rule. Okay. So so there are some key features of CTF. So the CTF is the ultimate low-rank decomposition method based on the full-rank covariance matrix over the whole complex spectrogram, right? So because the mixture data is decomposed into frequency and time covariance matrices. So more specifically, this can be interpreted as maximal likelihood estimation of a composite Gaussian process. And also, there is an equivalent formulation in any linearly transformed space. So, I mean, so currently, we assume that the decomposition is performed in the time frequency domain. However, this decomposition, the equivalent decomposition, can be performed in any linearly transformed space. So this can be feasible even when any Fourier transform is not used. So I mean the decomposition can be directly applied to the time domain signal. So this is very interesting. So and this feature indicates that the CTF model can deal with phase information directly. However, the problem is that the problem of CTF is the very huge computational cost. So in NMF, the time complexity is linear, the KFT. However, the computational cost of CTF is K F cube T cube. So it's impossible in reality, right? So that's why we need some acceleration technique to solve this problem. So before that, and going into the acceleration, let me introduce the probabilistic model behind the Itakura-Saito NML. So here, the power spectrum density is assumed to be given by using these equations. So W is the basis, H is an activation. So calculating such a product, we can get such a power spectral densities in the time frequency domain, right? Because this is frequency, this is time. So by calculating the product, we can get the rank one matrix, rank one power spectral density. So that, I mean, this power spectral density is represented by a rank one matrix. Then the complex spectrogram is generated, stochastically generated according to this complex Gaussian distribution, whose covariance, whose variance is given by this. So here, please note that, so this stochastic process is performed independently for each time frequency beam. So this means that, so the complex, this is the univariate complex Gaussian distribution. So univariate. So this means that you can focus independently on each time frequency beam. So here, for example, the power spectral density of this part is given by this, and then the complex value, the STXT coefficient of this point is stochastically generated according to this Gaussian distribution. And finally, the STXT coefficients, SFT, at time frame t and the frequency being f is given by the sum of these three STFT coefficients. So here, using the reproductive property of the Gaussian distribution, the mixture coefficient SFT is given by this equation. Okay, so because the SFT is the sum of z, so this means that the variance of this Gaussian distribution is sum of these power spectral densities. So this is a probabilistic model of Itakura-Saito NMF. So once such a statistical model is given, we can perform maximum likelihood estimation for parameter estimation. So here, SFT is a mixture. This is observed data. So given this data, we can maximize this generative probability by adjusting the parameters. So this is the maximum likelihood estimation. So, so this function is the likelihood function of these two parameters for observed data SFT. So the next one is the probabilistic model of PSDTF. So here, the spectral densities of a particular time frame t are simultaneously determined by this equation. And the, I mean, so in NMF, each time frequency beam is independently determined. On the other hand, in this method, the complex spectrum at each time frame is stochastically generated according to this complex Gaussian distribution, whose covariance matrix is given by this. So this is the covariance matrix. And this is a multivariate complex Gaussian distribution. So this means that the F elements of this vector are correlated with each other. So this means that in PSDTF, the frequency domain covariance structure can be dealt with in this formulation, thanks to the covariance modeling capability of the multivariate complex Gaussian distribution. And finally, the mixture spectrum is given by this complex Gaussian distribution. So this is the likelihood function. The maximal likelihood estimation is feasible by maximizing this likelihood function. And finally, this is the probabilistic model behind the CTF. So here, the whole complex spectrum over the time frequency domain is stochastically generated according to this complex Gaussian distribution, right? So this is the F by F matrix. This is T by T matrix. So here, this is a Kronecker product. So this is the FT by FT huge matrix. So using this multivariate complex Gaussian distribution, we can get FT dimensional complex vector. So this is a vector obtained by serializing all the time frequency bits of the complex spectrum. And this is likelihood function. Yeah, so this table shows a comparison, a mathematical comparison between these three models. This is NMF, this is PSCTF, this is CTF. So you can see a very clear correspondence among these three methods. Okay, so let's go back to the basics of CTF. So this model, so this is our mathematical formulation of CTF. So this is a reconstruction obtained by using basis frequency covariance matrices and the basis time domain covariance matrices. And the X is the observation. So here, so X is obtained by this equation. So S is a serialized vector. So and now we use the log determinant divergence as the evaluation criterion between the reconstruction and the observation. So so now let's discuss how to reduce the huge computational cost. So to do that, we propose a fast correlated tensor factorization, fast CTF in short. So here, this is the special case of CTF. So we introduce some additional constraints into CTF to get this special case. So what is a constraint used for fast CTF? So this is a joint diagonalization constraint. So here, we assume that frequency domain covariance matrices are jointly diagonalizable. So like this. So there are k sources, k components. So each basis matrix is assumed to be decomposed like this. So here, a P is some non-singular matrix, and this one. So this parenthesis indicates the diagonal, indicates some diagonal matrix here. So this is diagonal matrix. So P is some transform matrix called diagonalizer here. So P is shared all sources, all components, and only the diagonal elements are different among different sources. So this is a joint. This is called joint diagonalization. In the same way, the time covariance matrices are assumed to be jointly diagonalizable like this. Okay, so that's it. So this means that we restrict the degree of freedom of the model by using this constraint. So that's why the fast CTF model is a special case. constrained version of original CTF based on this joint diagonalization constraint. Okay, let's move on the probabilistic modeling of fast CTF. So I already explained the probabilistic model behind standard CTF. So this is a likelihood function used for standard CTF, right? And then we let's substitute the joint diagonalization constraint into this. So this equation is obtained by just substituting the constraint like this. So WK is assumed to be like this. So HK is assumed to be like this. So here, this is a Kronecker product. So this can be related like this. And finally, we can obtain an equivalent formulation like this. So here, so this is the linear transform of the original observation S. So this is the multivariate complex Gaussian distribution. But please note that the covariance matrix is given by a diagonal matrix. Okay, so this is diagonal matrix, this is diagonal matrix. So the Kronecker product of these two diagonal matrices yields some diagonal matrix. So this means that in this Gaussian distribution, all the dimensions are independent. It's so important. So here, S is an observed mixture, right? So S is, please remember that S is obtained by serializing all the time frequency bins of the mixture. So of course, all the time frequency bins are correlated with each other in the original time frequency domain. However, by transforming the original observation S by using this equation, in the new domain, all the bins are independent. It's so important. This means that we can ignore phase information in this new domain. This means that we can focus on only the power spectrum of the mixture in the space transformed by P and Q. Here is a figure showing multi-way space transform behind the CTF. So here, in CTF, each axis of input data is linearly transformed. So this means that we want to find a better space satisfying independence and low rankness. Okay, so this is a formulation of fast CTF. So this was already derived in the previous slide. What does this mean? So this is a linear transform. So this is the product of some matrix and the vector. So this is the matrix representation. So these two representations are equivalent. So S is a matrix representation. S is a standard complex spectrogram. So F by T a matrix. And the P is an F by F matrix. And using this P, you can get another, you can transform this observed mixture into another domain. So this is PS. In the same way, if you have some transform matrix Q, this Q is T by T matrix, using the product, calculating the product between Q and S, you can obtain another, you can transform this observed mixture into another domain. So integrating these two domains, we can get a new domain. So that the size of this representation is the same as the original representation. However, this is not a frequency axis. This is not a time axis. Okay, so because both the frequency axis and the time axis are transformed into different domains by using some transform matrices P and Q. So this is called multi-way space transform. And in this domain, all the FT beans are independent because the covariance matrix is a diagonal matrix. So this is so important. In this original domain, all the TF beans are dependent. However, in this new domain, all the TF beans are independent. So this means that we can ignore phase information in this new domain. So this means that we can perform very computationally efficient Elliptically NMF in this new domain because we are allowed to ignore phase information. So the computation is pretty fast in this new domain. The problem is how to discover such a representation, such a new domain. So if you are given P and Q, you can compute lightweight Elliptically NMF in this new domain. The remaining problem is how to find such multi-way space transform. Okay. So to do that, we use independent vector analysis. So here, so as I explained, that in this new domain, you can perform computationally lightweight Elliptically NMF for updating W and H, so NMF components. Okay, so how to estimate P? So it's very interesting. So here we assume that there are F-channel signals. Actually, this is the CTF or fast CTF are used for single channel blind source separation. However, in this case, so in the parameter estimation, we assume that there are F-channel signals. Okay, so there are F-channel signals like this. And so F-channels are separated to F sources in a determined setting. So the number of sound sources are assumed to be equal to the number of channels. So this is determined condition. To do that, we can use a technique developed for independent vector analysis. So IBA is one of the very popular techniques for multi-channel blind source separation. So here, such a multi-channel blind source separation technique is used for solving, for estimating the transform matrix P here. On the same way, the Q time axis transform matrix Q is also estimated by using the independent vector analysis. Okay, so using two kinds of IBA, we can get a new space where all the elements are independent, right? So IBA, independent vector analysis is an extension of independent component analysis. So ICA and IBA are used for so estimating independent sound sources from the mixture. So such techniques are very useful for estimating independent components, even in the single channel BSS. That's the idea. Okay, so let's move on to the multi-channel BSS part. Okay, so first, let me introduce briefly the background of multi-channel BSS. So this is the BSS is very important for various audio-related systems, including smart speakers and home robots, because they are, there are some important functionalities, such as speech enhancement, speaker identification and diagonalization, and acoustic event detection and sound scene analysis. So as a front end of these applications, the blind source separation is very important. So the conventional BSS technique is based on the short-time frequency transform, as in the single-channel BSS, right? So now, suppose that there are 3-channel observed signals like this, then you perform the short-time frequency transform to each channel, and then get 3-channel spectrogram like this. So, and also typically you assume that all the time frequency beams are independent, and only the channel inter-channel covariance structure is considered, right? So here XTF is a vector, m-dimensional vector, because now we assume that there are m channels. So this is an m-channel complex vector. So here, the phase information can be dealt with in this formulation, because actually we can deal with the complex values. However, all the time frequency beams are still assumed to be independent. This is a fundamental problem of typical blind source separation. Okay, so this is a very strong motivation. So conventionally, only the inter-channel covariance structure is considered. However, we aim to consider the full covariance structure in the time, frequency, and channel domain. Actually, this is a tensor data, so where all the elements must be dependent on each other. So such dependency covariance structure must be useful for improving the performance of one-channel blind source separation. So that's an idea, motivation. Okay, so this is a key idea. So we extend the idea of fast CTF to multi-channel scenario. So as in CTF model, fast CTF model, we can transform the frequency axis by using this transform matrix P, and we can transform the time axis by using this time transform matrix R. And also, we can transform the channel axis by using a set of spatial transform matrices. So actually, these transforms are performed independently for individual individual frequency beams. So using these 3 kinds of transform matrices, we can get new representation of observed data. So here, in the original mixture, this is the original observed mixture. So all the time frequency channel beams are dependent on each other. In contrast, in the transformed domain, in the projected mixture, all the elements are independent. So for this independent data, we can perform very computationally efficient non-negative tensor factorization. So, and also, this is the, this transform. So how to represent this linear transform? So this is the, okay, so this is a tensor data, but you can serialize all the elements, like all the elements of this tensor data. And then you can get a very huge long complex vector X, so TFM dimensional vector. So this means that the transform matrix is given by TFM by TFM matrix. So, okay, so this is a linear transform. So this linear transform matrix is determined by this equation. Actually, this equation includes time domain, time axis transform, channel axis transform, and the frequency axis transform. So this is a genuinely independent component analysis. Okay, so so let me briefly review the basic of probability of Marchand BSS. So now, suppose that there is a single sound source here, and there are two microphones here. So after a sound propagation, you can get such two-channel complex spectrogram. And here, if you focus on if you focus on some time frame t and the frequency being f, you can get two-dimensional complex vector x1 tf. Because here, this is source one. So this means that's why we use index one here. So anyway, so this is the two-dimensional vector. So if you plot this on this plane, first channel, second channel, so this this x1 tf is distributed like this. So typically this distribution is assumed to be a Gaussian distribution, multivariate Gaussian distribution. So here, lambda 1 tf is a power spectral density. This is non-negative value, and the G1f is a spatial covariance matrix. So G1f determines this elliptical shape, elliptic contour of this Gaussian distribution. And the lambda 1 tf is the scale of this Gaussian distribution. So this is a very basic formulation behind Marchand BSS. So if there is another sound source here, this is a second sound source. The second sound source has a different, this x2tf is differently distributed like this. So, okay, so this is a spectral density. This is the spatial covariance matrix. So what happens if two sound sources simultaneously occur? So, okay, so this is xtf is the sum of these two complex vectors. So in this case, using the reproductive property of the Gaussian distribution, so xtf, the mixture is given by this multivariate complex Gaussian distribution. Okay, so its covariance matrix is given by the sum of the individual covariance matrices corresponding to the individual sound sources. And here, this is a mixture observation. So this means that this is the likelihood function of these unknown parameters for the observation. So in terms of maximum likelihood estimation, we want to maximize the generative probability given by this likelihood function by tuning the values of these unknown parameters. Okay, this is maximum likelihood estimation. And okay, so in this framework, the one of the most popular, well-known methods is multi-channel non-negative matrix factorization. So here, power spectral density lambda 1 tf is assumed to be represented according to non-negative matrix factorization. So So this is the part spectral densities of the first sound source and the second sound source here. So the part spectral densities of the first sound source, for example, is assumed to be represented by using a set of basis vectors and a set of activation vectors in the framework of NMF. So this part is called a source model. Source model, okay? So source model is formulated in the single channel in the single channel domain. And then using some spatial covariance matrices G1 and Gn. So n is the number of sound sources. So you can get the source. You can get the source images. So this is merge channel. Okay. So this is the single channel power spectral densities. But this is the multivariate Gaussian distribution. And using this distribution, you can get merge channel source images. And finally, summing all these source images, you can get the observed mixture. This is a generative story behind multi-channel NMF. So this is the likelihood function. So the objective of multi-channel NMF is to find lambda and G at the same time. And then, however, the multi-channel NMF is computationally very heavy. So to solve this problem, the independent low-rank matrix analysis was then proposed. So in this model, the same source model is used. So that the part spectral densities of each sound source is formulated according to NMF. It is exactly the same as NMF. However, in this model, this spatial covariance matrix is assumed to be a rank 1 matrix, rank 1. So this means that, so this is, ILUMA is a special case of multi-channel NMF. And also, due to the rank 1 constraint, so this method is available only under a determined condition, where the number of microphones is equal to the number of sound sources. However, this method is very strong to initialization. This means that ILUMA is experimentally proven to outperform original multi-channel NMF. And recently, the first MNMF was proposed. This is the state-of-the-art method in the thread of BSS research. So in this method, the source model itself is the same as a multi-channel NMF or ILUMA. So here, the constraint on spatial covariance matrices is different. In this case, in this model, these spatial covariance matrices are assumed to be jointly diagonalizable. This is the only difference between these methods. And this is the likelihood function. So this likelihood function is maximized by tuning these unknown parameters. Okay, so this is a comparison. So multi-channel NMF has no constraint. So this means that the degree of freedom is the highest. So this has very high expressive power. However, due to the high degree of freedom, the parameter estimation is very difficult in reality. On the other hand, ILUMA has a limited degree of freedom, but it is relatively easy to avoid but local optima in iterative optimization of parameters. So first MNMF is an intermediate model between multi-channel NMF and the ILUMA. So because special covariance matrix is a full covariance matrix, the ILUMA is as in ILUMA, the special covariance matrix is a rank 1 matrix. So it's too strong. So this means that this model cannot deal with deverbalization at all. So it's too strong assumption in the real world. So that's why the intermediate model, first MNMF, is very important. And it is experimentally confirmed that this model works best in these 3 models. Yeah, so the first MNMF is the spatial is a combination of spatial transform learning and non-negative tensor factorization. So okay, so conventionally only the inter-channel covariance structure is considered. So here in this model, using a set of spatial transform matrices, we can obtain a new domain in where all the elements are independent. So this XTF is projected into another domain by using this equation. So this is a multi-channel NMF formulation in the original domain, right? So this is the this part is a spatial covariance matrix. So let's assume that let's use this joint diagonalization constraint. So all the spatial covariance matrices of all sound sources are assumed to be jointly diagonalizable like this. So now let's substitute this constraint into this. So here, this is equivalent to this equation. So in this projected mixture, this projected mixture is assumed to follow this multivariate Gaussian distribution, whose covariance matrix is a diagonal matrix. So this means that all the elements are independent, right? So in this domain, you can perform non-negative tensor factorization by ignoring the phase information and the correlation structure completely. So this is why the first MNMF is a fast, accelerated version of original multi-channel NMF. Okay. However, first multi-channel NMF is okay. It's beautiful and useful in practice. However, only the inter-channel covariance structure is considered. Our ultimate goal is to deal with the full covariance structure in this tensor data. This is the ultimate goal. So how to deal with the time frequency spatial covariance structure in a unified manner? Let's unify together the single channel and the multi-channel blind source separation method. So now, recently we proposed the first MCTF. So this is a combination of CTF. This is the state-of-the-art blind source single channel blind source separation technique, and the first MNMF. This is the state-of-the-art multi-channel blind source separation method. So you combining these 2 methods together, we can get the ultimate model in the multi-channel context, right? Okay, so first MCTF is the time frequency spatial transform learning and NTF. So as we already explained, the this observed mixture, original mixture, is transformed into another domain by using this equation, where the transform matrix is given by this equation. So where the time domain transform channel domain transform and the frequency domain transform are incorporated together. So, okay, let's substitute this. So this means that this projected mixture, this is a very huge long complex vector, is assumed to follow this multivariate complex Gaussian distribution, where the covariance matrix is a diagonal matrix. So this means that in this new domain, all the free elements are independent. Okay, so as in the first CTF, for parameter estimation, two steps are iterated until convergence. In the first step, we perform transform learning. So in this first step, we have to estimate P, R, and Q one by one by using the technique of IBA as used for first CTF, right? In the second step, given the optimized multi-way transform matrix P, R, and Q, the remaining problem is to update the NMF parameters and NTF parameters, more precisely speaking. So this can be efficiently performed by using the well-known multiplicative update rules. Okay, so this is a fine summary. So in this talk, we have introduced several single channel and multi-channel blind source separation method. So, and among these methods, the first MCTF is an ultimate model that can deal with the full covariance structure in the time frequency spatial domain. So this figure shows the comparison between existing and the state-of-the-art models. So there are two types of covariance modeling. The one is a full covariance model, and the other is joint diagonalizable covariance modeling. So, and in reality, this first version based on joint diagonalization constraint is useful because this full covariance model is computationally prohibitive in reality. So this is more useful in practice. And the first MCTF is the ultimate model that can consider both frequency covariance, channel covariance, and the time covariance. Okay, so finally, let me introduce the unified view of existing BSS methods. So this is a very fine, this is a more complete organization of existing BSS methods. So there are three ways: the temporal covariance, time frequency covariance, and the spatial covariance. And there are three levels of degree of freedom in each axis. So that if you incorporate any constraint, the covariance matrix is an unconstrained full rank matrix. Or you can restrict each covariance matrix to a rank 1 matrix, as ILUMA does. As an intermediate constraint, you can incorporate a joint diagonalization constraint. So by combining these strategies, you can freely design your own model by tuning the degree of freedom of the a probabilistic model used for multi-channel BSS.
So my name is Kohei Seguchi. In this section, we will focus on fast MNMF and its extension for joint blind source separation and de-reverberation. So as explained in the previous section, we formulate a probabilistic model of multi-channel observation, XFD, by using source model and spatial model. In fast MNMF, NMF-based source model and jointly diagonalizable spatial model is used. So the probabilistic model of single channel source vector is given by NMF like this, and the multi-channel source image is given by jointly diagonalizable spatial model like this. So the model of observation XFT is given by this expression. So in the jointly diagonalizable spatial model, the spatial covariance matrix SCM, which represents relationship between some sources and microphones, is assumed to be jointly diagonalizable, like these expressions. So first, I will talk about the interpretation of the jointly diagonalizable full-rank spatial model. As a first step, I will talk about the conventional rank 1 spatial model. Independent low-rank matrix analysis called UMR is based on the NMF-based source model and rank 1 spatial model. So the probabilistic model of XFD is given by this expression. So the difference between fast NMF and UMR is only spatial covariance matrix. It is assumed to be rank 1 in this method. So in the rank 1 spatial model, time invariant linear system is assumed. So the multi-channel source image XNFT is represented by this expression. So SNFT is the end source signal, and ANF is called a steering vector and represents the sound propagation process between N sound source and microphones. So when we assume SNFT follows complex Gaussian distribution like this, XNFT follows multivariate complex Gaussian distribution. Here, ANF Hermitian transpose of A is called a rank 1 spatial matrix. So this is a rank 1 spatial model. And next, I will explain about the implicit assumption of the rank 1 spatial model. In the rank 1 spatial model, one time frequency bin of observation XNFT corresponds to one time frequency bins of source signal SNFT, like these figures. This indicates reverberation is short because if reverberation is long, a one-time frequency bin of X observation X depends on the multiple TF bins of the source signal Sn, and XNFT is given by this expression. This model is called a moving average MA model. So ANFL indicates how much SNFT minus L has effect on XNFT. So and ANF0 SNFT represents a direct signal, and for L larger than 0, ANFL SNFT minus L represents the reverberations. And the probabilistic model of XNFT is given by this expression. In case of the jointly diagonalizable spatial model, we can get the physical interpretation by considering the MA model. So according to the definition, the spatial covariance matrix of jointly diagonalizable spatial model is given by these expressions. And this expression can be rewritten like this. Here, UFM is the nth column vector of Q inverse. On the other hand, in the MA model, the spatial covariance matrix is given by these expressions. So in both models, the spatial covariance matrix G and F is represented by the weighted sum of multiple rank 1 matrices. So from this similarity, this UFM is expected to play a similar role as ANFL. So in other words, sum of UFM represents direct paths and other UFM represent reverberations. So jointly diagonalizable spatial model can represent reverberant signals, unlike rank 1 spatial model. Another advantage of the jointly diagonalizable spatial model is it can represent the diffuse noise, which is often assumed to have full-rank spatial covariance matrix. Based on the interpretation of the jointly diagonalizable spatial model, we proposed a small extension of fast MNMF called rank constraint fast MNMF. We can specify the rank of each SCMs by initializing G tilde in a specific manner. So this is because from these expressions, the rank of the SCM depends on the number of non-zero elements of G tilde and F. And because the update rule of G tilde is given by this expression, once G tilde becomes 0, it keeps 0. So as a result, initial value of G tilde decides the rank of SCM. This is useful for appropriately reducing the degree of freedom and making parameter estimation stable. For example, in speech enhancement in non-reverberant conditions, we can reduce the degree of freedom by restricting the spatial covariance matrix of speech sources to rank 1 matrix. Next, we extend this fast MNMF for joint blind source separation and de-reverberation. So in the first MNMF, reverberations are regarded as a part of source images, and the separated signals include reverberations. But the reverberations are harmful, for example, for speech recognition. So for joint source separation and de-reverberations, the target diode signals and reverberations are separately modeled. The problem is how to formulate reverberations. One naive approach is using a moving average model. But in this work, we use autoregressive moving average model, ARMA model. So that this expression is a MA model, but this expression can be rewritten by this expression. So this expression means the beginning of the reverberations are represented by the MA model in a source-wise manner, and the remaining reverberations of all sources are represented by the AR model as a whole. So this equality holds for a specific B, but for other B, the AR model represents long reverberations. This is because by substituting X into this expression, we can get these expressions. This means AR model can represent infinitely long reverberations. So this is the advantage of using AR models. So from the expression of ARMA model, we can get the probabilistic model of XFT by these second expressions. This model is based on rank one spatial covariance metrics. But in this work, we replace these rank one SCMs by jointly diagonalizable full rank matrices. This is because the jointly diagonalizable full rank SCM can deal with diffuse noise, unlike rank one spatial covariance matrix, and we can derive the efficient update rules. So as a result, the probabilistic model of observation XFT is given by this expression. So the single channel source spectral is given by the NMX source model, and the direct signal is given by the jointly diagonalizable spatial model, and reverberations are given by the MA model and AR models. The parameters are estimated so that the log likelihood is maximized. And the target direct signals are obtained by using Wiener filter. So we evaluate AR, MA, fast MNMF using mixtures of two species and diffuse noise. We compared AR, MA, and AR, MA, fast MNMF with vanilla fast MNMF, vanilla ILMA, and AR ILMA. This AR ILMA integrates ILMA and AR reverbation models. As our evaluation metric, we used signal to distortion ratio, SCR. The upper figures shows the result when the number of microphone M equals 3, and lower figure shows the result when M equals 8. In both cases, the result of AR-MA fast MNMF outperforms AR and MA fast MNMF. This indicates both MA and AR models worked effectively. And by comparing AR fast MNMF and AR ILMA, AR fast MNMF outperformed AR ILMA. This is because the jointly diagonalizable spatial model used in fast MNMF can deal with diffuse noise, unlike rank one spatial model used in AR ILMA. Finally, let me show you the example of the proposed AR-MA fast MNMF. So this is observations.
The decline in the dollar and the continued strength of the economy, however, are now adding demand and causing those prices to rise too.
Sometimes better than competing US goods.
And
Change didn't come about
coincidence.
overnight, but after a few years, Americans recognized that Japanese products often were every bit as good and sometimes better than competing US goods.
And the result of conventional fast MNMF is.
Change didn't come about overnight, but after a few years, Americans recognized that Japanese products often were every bit as good and sometimes better than competing US goods.
The separation performance is okay, but the separated signal includes reverberations. And this is the result of AR-MA fast MNMF.
Change didn't come about overnight, but after a few years, Americans recognized that Japanese products often were every bit as good and sometimes better than competing US goods.
So as you hear, the reverberations are removed. So conclusion, so in fast MNMF, reverberations are regarded as a part of source images, and the separated signals include reverberations, but they are harmful for example, speech separation, speech recognition. So for joint source separation and de-reverberation, reverberations are explicitly represented with the AR-MA model, and jointly diagonalizable constraint is introduced to derive efficient update rules and deal with diffuse noise. That's all for my presentation. Thank you for your listening.
Okay, so hello everybody. My name is Mathieu Fontaine. So today I will introduce also FastMNMF, but using another probabilistic models than the Gaussian one, based on heavy tail model. So in that case, we will use a Gaussian scale mixture model. So first of all, let me give a very brief introduction that is linked to what the other participant explained. And then I will introduce the Gaussian scale mixture, explain how we can estimate the parameters, and propose two applications to what we call generalized hyperbolic FastMNMF and the generalized Gaussian FastMNMF also. And let me show a result of speaker separation experiments, and I will finally conclude that presentation. So that work is related to a paper that we submit a few months ago, 1 month ago, I guess, and that it's currently in review for TSLP. So first of all, a brief introduction. So my work in that presentation is based on what is multi-channel blind speech separation. So the goal is to extract speakers. So using the short time frame transform domain, where we assume we have an observation that is equal to the sum of speakers plus a noise component. Okay, so in general, we propose a Gaussian model. So what can be the drawback of light tail models? So Gaussian models is called light tail models. So in a few words, the light tail models is, if you consider the exponential distribution, light tails means that the tail of that distribution is always lower than the exponential. So heavy tail is basically above. So some works in 2008, for instance, showed that the initialization is sometimes tricky for the non-negative matrix factorization. So here, or we can say the power spectral density in a few words. Also, the light tails have some problem is that it's less robust. We're using some light tails distribution can have some problem because we have less robustness against impulsive noise. So basically, if I clap my hands and so on. And also for uncommon scenario, for instance, for some, if in the training set, you don't have some noise and suddenly you have a noise in the, so for instance, imagine you have a music noise that was not in your data set, you can have more problem during the test set if it's not in the training set. So there is also some works, if you're interested in, that suggest to use heavy tails models for gradient descent algorithm in a deep neural network approach. But in that presentation, I will not focus on deep neural networks, but this is just for your information about why heavy tail models can be interesting. Okay, so first of all, let me introduce what is a Gaussian scalar mixture. So the Gaussian scalar mixture, in fact, is, I think, quite easy to understand compared to the Gaussian model. It's a Gaussian where the covariance is randomly perturbed by what we call an impulse variable. So the impulse, so basically, informally, conditionally, we have a Gaussian distribution knowing that impulse variable. So here is the perturbation of the covariance. The impulse variables in the non-negative variable, so it means that the support of that variables is between 0 to plus infinite. And in fact, that model includes a lot of well-known heavy tail extension already. So one example that maybe is not the most common one, but include already a lot of common one, is a generalized hyperbolic distribution that were proposed in the 70s or 80s. In that case, the impulse variable phi is known. This is a generalized inverse Gaussian distribution. And the probability density function of such generalized hyperbolic distribution is also known as follow, where we have here the modified Bessel function of second order, of second kind, sorry, of order eta minus m. So here eta and alpha control the heaviness of the tail. And here we have what we call the shape parameter and covariance matrix or shape matrix. It depends of which model we have. So two examples is one is a generalized student T that is close to the classical multivariate student T distribution, but not exactly the same in a few parameters because we have the divided by 2 here. We have the Gaussian case, and we have also the normal inverse Gaussian case. There is also some other one like variance gamma, hyperbolic distribution, but I will not go too much in the details. That is already a lot of distribution, I guess. Another example of Gaussian scale mixture, well known, is the symmetric generalized super Gaussian distribution, where, okay, technically beta can be between 0 to plus infinite, but to be a Gaussian scale mixture, in that case, so to have impulse variables, beta has to be between 0 and 2. But in that case, we don't know the law of phi, so which can be inconvenient, but we will see later that it's not a problem for in our case. So the PDF is as follows. And beta is a shape parameter that controls the tail index. So basically how heavy is the tail. So if beta is close to 0, we have the heaviest one. And if beta is close to 2, we have beta equal to 2 is the Gaussian, and we have something light. And A here again is a shape matrix, except for beta equal to 2, we say covariance matrix. Another very well known is elliptically contoured alpha stable distribution. So alpha stable distribution is a very large family that satisfies the reproductive property in the sense that if we have a sum of alpha stable, it remains an alpha stable. But you have to be careful because the parameters of the sum is not equal to the sum of the parameters. But this is another problem. But in the case of elliptically, why we are interested in elliptically contoured alpha stable distribution in general, it's because we can also develop a model with a perturbed covariance matrix by an impulse variable. So here, this is the same. Alpha is between 0 and 2, and alpha, the smallest alpha, the heavier or the tail of the distribution. In that paper, so I will not go too further in the detail, but I also developed alpha AR fast MNMF. So basically, I combine what Sekiguchi-san proposed and alpha stable distribution, and alpha is estimated. And in that case, okay, phi is a positive alpha stable distribution, but the closed form of the PDF is unknown. And also, so phi is known. So phi is known, but we don't have a closed form. And this is the same for the PDF of U. This is unknown. And so, yes, the small video that was there is basically how to show how the sample of some data varies if I consider different alpha. So you saw that maybe if alpha start to be smaller, you have more outliers in our data. Okay, so this is a classical example. So just to summarize the plethora of fast MNMF variant that we can propose. So the one that I proposed in the past was the alpha stable fast MNMF. Those ones, Students T and GEG fast MNMF was proposed by Sarwatari Sensei Lab in Tokyo University. And so what I propose is to unify all those representation into one fast MNMF model that I call GSM, so Gaussian scalar mixture, fast MNMF. And here, this is basically summarized when we know the law and so on. So, okay, now I have my framework. So how I can derive my parameter technique that unifies all fast MNMF versions. So in a few words, so to summarize the probabilistic model, we have here we assume we have independent Gaussian scale mixture model on sources as follows. And so we assume that the covariance perturbation is the same for all sources. So you will see later why we propose this. This is there is some reason, especially to reduce to have a better algorithm performance, and also to propose a closed form multiplicative update rules. So the mixing model becomes as follow. Okay, so with the power spectral density and the spatial covariance matrix. So this is the same model as Sekiguchi-san or Yoshi-sensei showed before. So now we apply the joint diagonalization. So basically we have something like that with QF, so the diagonalizer that they introduced before. And in that case, so this is more or less the same, just we have a conditional Gaussian distribution with the parameter phi, so which are the impulse variable that we aim to estimate also. And in that case, we don't propose a Wiener filter, classical Wiener filter to estimate our sources, but what we call a marginalized Wiener filter. But in the fact, because phi doesn't depend on the sources, it's reduced to the classical multi-channel Wiener filter. And so we have many parameters to estimate. We have theta. So this is an MF, the diagonalizer Q, and the parameters or Gn, so of the diagonal of the spatial covariance matrix or spatial shape matrix, and phi that are the impulse variable. So now, just in a few words, how to explain how we estimate those parameters. We use a minorization maximization technique for the parameter estimation. So that function that maybe looks complex, in fact, is the same as in the Gaussian cans and how we derive the parameters. So the only difference that I here I show in red. So this is the only difference compared to the Gaussian part. So basically we have an expectation. So we will have a E step to do in order to estimate those expectations. Okay, so now the question is how we compute that expectation. So in fact, we show that you can have a closed form, in our case, with a phi that depends on f and t and not n. you have a relation between the probability of your observation, of your source image observation, and that expectation. And so basically, if we know the PDF, the log PDF, the derivative, sorry, of the log PDF, then we can find the expectation. So in fact, the knowledge of the law of phi is not necessary. This is just to show that we just need to know the log PDF. So this is the reason why I will not show you also some results in that presentation about alpha stable, because we don't know the log PDF. So in fact, to tackle that problem, we need to use a metropolis hasting algorithm that is time consuming and that is out of scope of that presentation. Okay, so just two examples of how it looks, the E-step for GH fast MNF and GG fast MNF. So generalized Gaussian and generalized hyperbolic. So in that case, the expectation have that form. And in GG, it has that form. Okay, and you can also show that the result coincide with the already proposed T fast MNF, so the student T fast MNF and Gaussian fast MNF. So we really summarize already proposed method and extend to some other method. The multiplicative update rules are really similar as Gaussian fast MNF, except we have that expectation. So that expectation here, 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 and here. So this is exactly the same, except we have that small coefficient, I would say, that appears, but that helps to have something more robust. Okay, so now let me show the results, quickly some results. So the data that I use is 2 and 3 speakers with different number of sources. And okay, in that case, I consider the signal to distortion ratio, signal to artifact ratio, and signal to interference ratio, which are very basic scores used in audio source, in blind source separation. The baseline method are the student T fast MNF, Gaussian fast MNF, and the GG fast MNF. And the one that I propose here is the normal inverse Gaussian fast MNF, so which is a particular case of generalized hyperbolic fast MNF model. So this is my settings here with 300 iteration of expectation maximization algorithm, and how I initialize my parameter. Sorry. So the performance, as you can see, in general, the normal inverse Gaussian in many cases, so for the SDR, slightly outperform the proposed method. But you can, if I detail the SAR and SIR, sometimes the SAR, so in general, so the SAR is lower. So one reason is maybe the modified Bsa function calculation. Sometimes, so first of all, it's heavy and it's approximate. And so with some specific data, sometimes doesn't give a good estimation. So I guess that if we can improve that part, I guess we can get better results and less artifact. So, but surprisingly, yes, the best SAR is in general for T fast MNF, so for the student T fast MNF. Okay, just a very brief speaker audio demonstration. So this is what we aim to separate.
The obviously Russians were closed Friday, saying no to the cultural barbarian prices.
This is the first speaker.
Notes from the front, colon. The same broker put me on hold early in the phone call, period.
The second speaker.
European stock markets were closed Friday and Saturday, except Milan, where prices edged up.
The third speaker.
He obviously relishes a good fight, and saying no to the cultural barbarians and the current wisdom.
Okay, so I will just give two examples. So first, the Gaussian fast MNF.
Notes from the front, colon. The same broker put me on hold early in the phone call, period.
So the separations is quite well, but you can still hear the other speaker behind this. The second speaker.
European stock markets were closed Friday and Saturday, except Milan.
Okay, so that one, basically, we have more a mix, still a mix of several speakers. The third speaker.
He obviously relishes a good fight, and saying no to the cultural barbarians and the current wisdom.
This one is like the speaker one. We have a good separation, but still some part of the other speakers. Okay, just let me show quickly the proposed method.
Notes from the front, colon. The same broker put me on hold early in the phone call, period.
So here we can see that the impulse variable estimation, so the expectation, act like a kind of voice activity detection in our speaker setting. Now the speaker 2.
European stock markets were closed Friday and Saturday, except Milan, where prices edged up.
Okay, so we can distinguish more the speaker, even if it's still not perfect, but we have a better improvement. And the speaker 3.
He obviously relishes a good fight, and saying no to the cultural barbarians and the current wisdom.
Okay, so it was the result. Okay, now let me conclude quickly my presentation. So as a conclusion, we propose in that work an extension of Gaussian fast MNMF to a very large family of heavy tail distribution called Gaussian scalar mixture. And so we propose Gaussian scalar mixture fast MNMF that outperforms the state of the art, giving the good set of parameters, and that in a sense easy to implement because we just have to compute one expectation, and so to multiply by that expectation in the multiplicative update rules. Some future works that I can propose in a brief. So about the current parameter model, we can try to improve the normal inverse Gaussian estimation by maybe smoothing the parameters, so using some window. Replace the modified Bessel function estimation by a faster or more stable one. There is currently some paper that explain how we can improve that modified Bessel function estimation. Also, we can propose some deep neural network extension that I guess Harrison and Banderson will explain better than me, but we can replace the NMF speech model by a heavy tail deep speech prior. So this I work on that part with the Cauchy model. So this is an alpha stable case. This is basically, we replace the power spectral density by deep neural networks. Or using, so what Harrison will propose, a normalizing flow. Apply either on a fast MNF or IVA or something else decomposition, so that basically we can have another spatial model estimation using so that new technique called normalizing flow. Okay, so that's all for me. Thank you for your attention, and please, if you have some questions, they are of course welcome.
Thank you, Matthew.
Thank you.
Okay, so in his talk, we gave our extension, detailed extension of fast MNF model. So yeah, this is another way of extension of fast MNF. So these two previous talks are orthogonal, I think.
Mm-hmm.
So extension for joint dot separation and de-separation, and the extension for making the model more robust to realistic signal. So if you have any questions or comments, please write on chat. Okay, thank you, Matthew. Let's move on to the next speaker.
Thank you.
Hello, everyone. My name is Yoshaki Bando, and I'm a visiting researcher at AIP, and mainly working on AIST Sansoken at the AI Research Center located in Odaiba, Tokyo. So today, I'd like to introduce semi-supervised source separation by using deep source models. So this talk focuses on a source model of statistical multi-channel source separation. As the other presenters introduced, the recent source separation methods consist of source and spatial models. So in these presentations, the source model is formulated by a linear model based on a non-negative matrix factorization, NMF. In this presentation, we extend this source model to a nonlinear model based on a variational autoencoder, which has a high capability of representing complex source spectra. So more specifically, we model the source signal by using the deep generative model. In this model, we first assume a latent feature vectors Z following the standard Gaussian distribution. For example, if the source signals are speech, like this one, so the vectors represents speech characteristics. So like each column of this figure shows each vector, and each vector represents the characteristics of each frame as the pitches or envelopes. And we then transform this latent feature to the power spectral density, lambda, by using a nonlinear function, g theta f, which is a deep neural network. And that this theta represents the model parameters of the DNA. And then, as in the NMF-based source model, the source signals are generated by a zero-mean Gaussian distribution, like this one. And we can precisely represent the source vector density by using this neural network. We then think about how to train this deep generative model. So by using a dataset of clean speech signals, we want to train the generative model G such that the log marginal likelihood, this one, for the dataset is maximized. This problem is formulated by this one and derived from the integration of the product of this PS given Z and PZ. Since this integration includes nonlinear function G in the PS given Z, so this likelihood is intractable and hard to calculate directly. So to solve this problem, we train the deep generative model based on a variational autoencoder called VAE. So in the VAE, we introduce an encoder DNN, this one, QZ given S, to approximate the log marginal likelihood by taking its lower bound. So as in this inequality, we can take a lower bound of log marginal likelihood with this one. So the expected log likelihood and Kalbach-Leibler divergence between the approximated posterior Q and the prior distribution PZ. So since these two terms are easily calculated, we can train the encoder and decoder networks to maximize the log marginal likelihood by maximizing this lower bound alternatively. So then I explain an application of the deep speech model for speech enhancement. So this work is based on these three papers written by Sekui-san and me. So the speech enhancement is a task to extract speech signals from a mixture signal of speech and noise. It is used for a front end of automatic speech recognition and hearing aids. And it is also used for some tasks such as search and rescue tasks to find a victim calling for rescue. So like this illustrates, it is often difficult to assume the environment where they are used. So robustness against various acoustic environment is essential. A major approach to the speech enhancement is to use supervised neural network. So in this approach, the network is trained to this one. The network is trained to directly convert a noisy speech into a clean speech in a supervised manner. So due to this nonlinear mapping, they have excellent performance. However, they sometimes deteriorate in unknown noisy environments, which are not included in the training dataset. So to overcome this limitation, we develop a semi-supervised speech enhancement with deep speech prior. This is a hybrid method of a deep speech model and statistical noise model. So since we can use many speech corpus as training data, we model the speech signals with a DNN, actually variational autoencoder. On the other hand, noise training data are often few, so we assume a statistical noise prior, actually it is a non-negative matrix factorization model. By combining these models into a unified probabilistic model, we can extract the speech and noise in a semi-supervised manner. More specifically, we assume that the speech signal is generated by the VAE-based source model, and noise signals are generated by the NMF-based source model. So like this one, so the speech signal is generated by VAE, like this one, and noise is represented by the product of basis and activation vectors. And then these signals are, we apply a jointly diagonalizable model to these source signals to obtain the image signals and generate the observed signal by summing up these image signals. In summary, this model can be formulated by this generative model, and we can separate speech and noise signals by estimating the power spectral densities, lambdas, and spatial model Q and G. So then I report our experimental evaluation. So in this experiment, we evaluated the proposed method by using time-series noisy speech dataset. We used, especially we used 100 utterances from its evaluation subset, and it includes 4 types of noisy environments: on a bus, in a cafeteria, in a pedestrian area, and on a street junction. And we measured the enhancement performance by source to distortion ratio, SDR, which is standard criterion of source separation. And we also measured computation times for speech enhancement. I then show the enhancement performance in SDR. So these bars shows the SDRs of each method, and left is bad and right is good. So first, you can see that the first MNMF is better than the conventional methods of MNMF and EMA. Furthermore, the first MNMF DP, which uses the deep source model and it is a proposed method, successfully improved the SDRs from the original first MNMF and also from the MNMF and EMA. And I then describe the computational time of the method. So we measure the computational time for enhancing an 8-second speech signal by using NVIDIA Titan RTX GPU. So the computational time of first MNMF is drastically reduced from the MNMF and comparable to the ILMA. And also the time for first MNMF DP is increased from the first MNMF. This value is reasonable to obtain higher enhancement performance. So then I show you some examples of the enhancement signal. So firstly, this one is the observation.
A print media campaign will begin the following day.
And this one is the clean speech signal. That is the target one.
A print media campaign will begin the following day.
And this is the enhanced signal by the ILMA.
A print media campaign will begin the following day.
And finally, this one is the enhancement signal by first MNMF DP.
A print media campaign will begin the following day.
So you may hear that the proposed first MNMF DP clearly enhances the speech signal. And furthermore, this semi-supervised approach can also be used for enhancing monaural noisy speech signals. So in this case, the speech and noise signals are generated by VA-based speech model and NMF-based noise model, as in the multi-channel case. But the noisy speech is represented as a just sum of these source signals. Since the VA-based speech model has high capability to represent speech signals by using the pre-training, this source model can be used for monaural speech enhancement. So then I show some demo of this monaural method. So first, I show mixture signal, this one.
He was quickly barred from using it, touching off a series of appeals and reviews.
And this one is the enhanced signal.
He was quickly barred from using it, touching off a series of appeals and reviews.
So you may hear that even for monaural enhancement, the semi-supervised approach based on the VA-based source model works very well. So that's all. Today, I introduced the source modeling based on deep generative model and presented some applications to speech enhancement. Thank you.
Thank you, Bando-san. So his talk is about the extension of the source model based on a deep neural network. So actually, in my first talk, so I explained only the classical models without using the deep neural networks. But in the last two talks, the source and the spatial models are extended by using the deeper neural networks to improve the expressive performance of the model. Okay, so let's move on to the last speaker. Please start.
Okay, hello everyone. My name is Aditya Arinugraha. I am a postdoctoral researcher in the Sound Scene Understanding team. And thank you for staying with us until now. In this last talk, I want to present our work in unsupervised audio source separation with deep spatial models. This work addresses the problem of unsupervised multi-channel audio source separation. Nowadays, it's getting more practical and affordable to obtain multi-channel recordings because more devices are equipped with more than one microphones, such as smart speakers, IC recorders, and smartphones. One recording is a mixture of sounds from sources of interest, for example, speakers A, B, and C here, and sounds from interferences. In this example, the interferences may come from the office appliances, vehicles, or other conversation in the room. And multi-channel recordings also include spatial information that may reveal the speaker location or the audio source location with respect to the microphone array. This is because a signal from one source is received differently by different microphone. For example, just an intuitive example, sounds coming from speaker A are received by the microphones on the left louder and earlier compared to the microphones on the right. And we can exploit such spatial information for separating the sources of interest from the mixture. This is helpful for many applications, including automatic speech recognition and also human listening. We are interested in unsupervised or blind approaches because they are potentially better to handle unknown environments with unknown interference sources. The scope of this work is limited to the determined blind source separation. In this case, we want to recover n sources, knowing m observation captured by m microphones, where n equals m. This separation is also known as demixing process. And in the next slides, I will discuss the normalizing flow that we will use for the demixing process. After that, I will show the relation between normalizing flow and the determined blind source separation methods, such as independent component analysis and independent vector analysis, ICA and IVA. Finally, I will introduce a time-varying extension of IVA based on normalizing flow. We call it as NF-IVA. Let's start with the normalizing flow. Normalizing flow is a technique that can represent random vectors following a complex probability distribution in terms of another probability distribution, such as the standard Gaussian, using a series of bijective transformation. And the log likelihood of this complex distribution is then can be expressed as the sum of the log likelihood of the standard Gaussian and the log absolute determinant of the transformation. The mathematical formula is shown here. And in the context of normalizing flow, the bijective transformation is also known as flow step. And flow step may use nonlinear functions. In this case, particular network construction is necessary to allow simple computation of this determinant. This results in many normalizing flow variants such as the one shown here. Normalizing flow is related to the determined source separation. The determined blind source separation methods typically work in the STFT domain. So if we have multi-channel recordings, our STFT will have 3 axes. So we have frequency axis, microphone axis, and time frame axis. And determined blind source separation method typically work in time frequency binwise manner. So the input is the mixture vector XFT, where one dimension corresponds to one microphone, and then the output is a source vector YFT, where one dimension corresponds to one microphone. One source. The separation is performed by transforming XFT using the so-called demixing matrix WF that we need to estimate. So this WF basically performs spatial filtering. This is equivalent to a normalizing flow with a single flow step. So the log likelihood of this mixture vector is the sum of log likelihood of the source vector and the log absolute determinant of the demixing matrix. To optimize this WF, to estimate this WF, we can assume statistical source independence and then maximize the log likelihood. In ICA, time frequency bins Y and FT are assumed to be independent of each other, while in IVA, the vector Y and T are assumed to be independent. And in IVA, the demixing matrices, the WF, can then be optimized by maximizing this mixture log likelihood function taking into account all of data for all frequency bins and for all time frames. To emphasize, a determined plane source separation can be seen as a normalizing flow. Instead of using a single linear transformation as in the classical IVA, normalizing flow allows us to use time-varying linear transformation parameterized by nonlinear functions in order to better cope with possible data variation. And all parameters of the so-called NFIVA are optimized by gradient descent with backpropagation to minimize the negative log likelihood function. So we can say that this work introduces a spatial model based on neural network that follows the maximum likelihood principle. Let's discuss further the flow steps in this NFIVA. Our NFIVA uses two kinds of flow steps. The first one is time invariant projection, and the second is time varying scaling via event coupling layer. The time varying scaling is performed using the diagonal matrix over here, whose diagonal entries are estimated using feed-forward neural network denoted by omega here. And okay, so in IVA, we obtain YFT by performing multiple projection and scalings to XFT. And to maximize the mixture log likelihood, we have to take into account the log absolute determinant of the projection matrices and the scalings. Here we assume that its vector YNT follows the time-varying Gaussian distribution, whose variance is computed in the maximum likelihood sense as shown here. So the parameters to be optimized are the projection matrices, the W, and the MLPs, omega, the multi-layer perceptrons, omega B and omega A here. All of these parameters are initialized such that the NFIVA performs identity at the beginning to improve the optimization stability. And this is achieved by setting all the projection matrices, the W, to the identity matrix and zeroing all of the output layers. And the parameters are then optimized by gradient descent with backpropagation using Adam optimizer and learning rate decay and also gradient normalization. The loss functions to be optimized are either LNVP or LVP. LNVP is simply the negative mixture log likelihood function, while LVP is a variant in which we take into account, we consider volume preserving constraint. And to do so, for the projection matrices, we use this computation for multiple iteration to obtain the nearest orthogonal matrix. And for the coupling scales, we propose an L2 regularization term as shown here. So using these two approaches, ideally, the log absolute determinant here will be 0. We evaluated the proposed NFIVA for multiple speech separation tasks in reverberant environments with different number of sources, different number of speakers, and also different numbers of microphones. In the true determined separation case, we separate the actual number of sources, while in the pseudo-determined separation cases, we separate more than the actual number of sources. In this case, we then take the estimated sources with the highest energy before computing the performance matrix. In addition to the proposed NFIVA, we consider AUX IVA and IVA BP as our baseline method. So this IVA BP is basically an IVA, but the parameters are optimized by backpropagation instead of multiplicative updates as in AUX IVA. Here I show you the results, the experimental results. On the y-axis, I show you the signal to distortion ratio, the SDR, higher is better. And on the x-axis, we have the number of parameter updates. And the top figures, I show you the results for 2 speaker separation, and the bottom figures show those for 3 speaker separation. And the different column here shows the use of different number of microphones from 2, 4, 6, and 8. Overall, NFIVA VP, the red lines, outperforms the others. In this case, NFIVA NVP, IVA BP, and AUX IVA. And we can also see that NFIVA NVP, the one without volume preserving constraint, is performed similarly to the IVA BP. This indicates that the flow steps are useful, but to optimize them, regularization, in this case using a soft volume preserving constraint, is required. And we can also see from these results that AUX IVA does not converge well for the pseudo-determined cases. Then we can also see that the backpropagation-based methods converge well, but they require many parameter update iteration. That's why we compare the computational time for 1 parameter update for 1 second mixture. The values here are shown in milliseconds. The backpropagation-based updates are slower than the multiplicative updates in AUX IVA. And we can also see that because of the costly matrix orthogonalization, NFIVA VP is much slower than NFIVA NVP. And before concluding this presentation, let's listen to some audio samples. So this is a 3 speaker separation case with 6 microphones. To make this short, let me play only 1 speaker.
New York's body positive already. And higher interest rates attract foreign investors, pushing up the dollar. And higher interest rates attract foreign investors, pushing up the dollar. And higher interest rates attract foreign investors, pushing up the dollar. And higher interest rates attract foreign investors, pushing up the dollar. And higher interest rates attract foreign investors, pushing up the dollar. And higher interest rates attract foreign investors. New York.
Okay, to conclude, we recast determine blind source separation as a normalizing flow optimization problem. We then propose NFIVA, which is a time-varying extension of the classical IVA, and introduce a soft volume preserving constraint as a useful regularization. Then we show that NFIVA with volume preserving constraint outperforms the other compared methods, although it is computationally expensive. We need to address this in the future, including by exploring some initialization scheme, and then incorporating more advanced technique and more advanced source model as discussed earlier by the other speakers. So ultimately, by combining the techniques we presented earlier today, we want to have a methods with DNN-based source and spatial models that fully preserve the maximum likelihood principle. That's all from me. Thank you for your attention.
Okay, so that's it. So today, to summarize, today we gave some tutorials on blind source separation and the decompensation based on statistical models. So basically, our models are based on the multi-channel NMF or first version. It's first version based on joint diagonalization constraint. And this model is very useful and works very well in reality. And I will recommend you to use this technique as a baseline for your application. And at the research level, so this model can be extended to incorporate the power of new deep neural networks to extend the source and spatial models. And also this model can be extended to joint separation, de-evaporation, and denoising. And also, as Matthew explained, so the conventional Gaussian assumption can be replaced with more robust probabilistic model based on the Gaussian scale mixture representation. So these extensions are, so you can freely choose you can freely choose these extensions because these extensions are different ways, right? So basically these extensions are orthogonal to each other. So yeah, and we are now working on this kind of audio signal processing and its application to the real world and something understanding. じゃあ皆さんありがとうございました。お疲れ様でした。Thank you very much for your attention.